Well, first let me say that I'm very happy to be back in Sendai, which I've been to several times before, especially for the International Linear Collider. And of course, due to the pandemic, I haven't been to Japan for a few years, and it's very nice to be back here and enjoying both Japan and especially Sendai. We just heard an introduction by my former student, Hitoshi Yamamoto, and he covered an enormous amount of science. He told you about basically physics at very long distances, which we call astronomy, and he told you about physics at very, very short distances, which we call elementary particle physics. And the problem of elementary particle physics, as he pointed out, is now focused around the discovery that was made in 2011 at CERN of the particle that's responsible for mass in nature. That's obviously a very important concept. Mass is something we can all relate to. And now we want to understand what the process of making mass is really about, and not just that we identified the key to it, we now have to study it. And that's what the International Linear Collider is about. It's the ideal tool to do that. And so we worked very hard to design a machine that would be ideal for studying the Higgs boson, basically. And we found that an ideal way to build it was to use the technical skills in Japan, the will to take on a new project like this by the Japanese scientists, and a very attractive location in the mountains north of here. So we know what we'd like to do, and we're hopeful that the Japanese government will soon decide that this is a project they want to do, in which case I think many of us in the world community of physics will happily come here to Japan to understand what this mysterious process that creates mass in nature is really about. I'm going to talk about the other problem, which is physics at long distances, and I would say that Dr. Yamamoto talked about a lot that we've learned about astronomy, but that's all of it is based one way or the other in using some form of electromagnetic radiation. We began by using our eyes and studying the sky. Then, at the time of Galileo, we developed the ability to look with lenses and focusing it, telescopes, and do it better. And in the 20th century, we started doing astronomy by looking at not just visible light that we can see with our own eyes, but light that is in other wavelengths that are radio or gamma rays or infrared or now ultraviolet. And that has created a very rich science of astronomy and what we call cosmology, which is physics really of the early universe. As was indicated in Dr. Yamamoto's talk, this, though, represents only a small fraction of what's in the universe, even though we've learned so much. What I'm going to talk about today, which is gravitational waves, is a completely different subject. Everything we've learned in astronomy and astrophysics is based on electromagnetic radiation, and it accounts for only a few % of what's in the universe. Now, not what I'll show you today, but now we've opened the window to be able to look at the universe in a completely new way using gravity, something we can all relate to, instead of just electromagnetic waves. We all know gravity is very different than electricity. It's a completely different way of looking at the universe. And I think the underlying, I'd say, appreciation and excitement about the discovery of gravitational waves isn't that Einstein predicted them. That's important, of course. But it's because of the possibility to, in the future, to really learn about the universe in a completely new way. And I fully expect that that'll bring, just like astronomy has, a completely new view of what the universe is, how it began, and how it's evolved into where we live today. So I'm going to talk about how Einstein came about proposing gravitational waves, a little bit about the difficulty of detecting them and why it took 100 years, and something about what they look like and what we've seen so far, which gives us some new views of astronomy already, and just a hint at where it's going to go in the future in my short talk. So let me move forward. So I'll start historically, just as I said, by beginning with Einstein. Actually, maybe beginning a little before that to put Einstein in perspective. The most successful theory of physics ever was proposed in 1687 by Sir Isaac Newton, and that was the understanding of gravity. He put forward a theory of gravity. He called it universal gravity. I'll tell you why in a second. And he put this forward to explain everything about gravity. And that is, universal means what he tells us. It describes how the apple falls to the earth. It describes how the moon goes around the earth, or the earth around the sun, or anything else that involves masses and the attraction of masses. It involved a rather simple formula. I give it here. It's the force between two masses is the product of those two masses divided by the square of how far apart they are. And the strength of it is multiplied by a constant that he couldn't determine. And actually, it took another 100 years to tell what it is. I won't spend the time on that. This theory of gravity, when he put it out, he felt it would describe everything physically that we might see or measure that had to do with gravity. He solved the problem at the very end and felt he had a universal case for gravity in this formula, when it not only worked for what I said, the apple falling or the planets going around the Earth, but the problem of comets, which turns out to be even a harder one. And the fact that he could trace a comet properly by explain the trajectory by this formula gave him universal gravity. I said this is the most successful theory of physics ever, and that's true. He wrote it all up in a book called the Principia. It lasted in its form until 1915, when Einstein came along. But basically is still the basic theory of gravity for most of what we see and use in gravity in terms of everyday life. There's parts of the use of gravity that don't get quite explained by Newton's theory, and I'll point that out. And this is true of physics and science, I think, in general, but in physics, where we talk about theories of physics, one should realize that a theory of physics doesn't describe everything. It's always an approximation. It's the best we can do at describing whatever we're trying to describe. It's usually not wrong, but maybe limited in some ways. And we move on when we get a new theory that can not only do what the present theory did, but explain some things that the present theory didn't. And that's what happens in Einstein's theory. It doesn't make what Newton did wrong at all. It goes beyond that, and I'll explain to you how it goes beyond that, in addition to it being rather complicated. I show the formula, the basic formula equivalent to GMM over R squared for Einstein's theory. You can see it's a little bit complicated, and I'm not gonna describe it, but that's the equivalent. This theory is rather different in the way it's formulated. It's based on space and time itself, and basically it becomes one word in this theory. Space and time are unified together. That's a very difficult concept mathematically, and when they're put together, it becomes a theory that it includes acceleration, which was not included in his earlier theory of relativity. So Einstein in 1905 had a theory called special relativity. We've all heard of it, E equals mc squared. And what happens when anything goes very fast, the theory of relativity. He then added acceleration to that theory. And when he added acceleration, he came up with what is a new theory of gravity. So that's the transition. Let me say just a little bit more about it. So 1687, Newton described for us how the apple falls to the earth. Einstein then came along, and he said basically that gravity isn't a force. You'll notice when I wrote down Newton's theory, we wrote it as a force that was g m1 times m2 over r squared. And in Einstein's theory, it's not a force at all, but instead, masses act on space, something Dr. Yamamoto talked about, and time itself, and makes its impact on space itself. I show that in the picture here, that space-time tells us how mass moves. This is a quote of Wheeler, who was a physicist at Princeton University, that the presence of the sun, which is shown in this picture, distorted the space around it, like you see on the grid just below. And the Earth distorts it a little bit, as you can also see in the grid. And, whoops. And basically, the distortion of the space around it is the attraction of the Earth to the sun, so that the gravitational pull between the Earth and the sun happens because of this distortion of space and of time. That solved, once this theory came out, it solved the only known problem that existed in Newton's theory. So in 230 years, only one small deviation from his theory had been observed, and that was the orbit of Mercury around the sun. The orbit of Mercury around the sun is very elliptical, as I show here, and because of the positions of all the planets and moons, each time it goes around, it goes forward some amount that's calculable using Newton's theory, for example. And you calculate from Newton that it should move forward by 532 arcseconds per century. That's just a number you can calculate. And actually what was observed was about 10% larger than that. So Newton's theory worked on absolutely everything except a 10% discrepancy. That discrepancy could have been fixed if there happened to be some mass between Mercury and the sun. And that was proposed and looked for, but nobody had found it by the time of Einstein's development of his theory of gravity. It was actually looked for even more later by NASA, but nothing was found before. The first thing that Einstein's new theory did was get the right answer for, or let's say the answer that is what nature does. It gets 575 arcseconds per century. That, of course, made Einstein feel that the theory was right. And when he presented the theory for the first time in 1915 to the German Academy of Sciences, this is what he showed, that it predicted the orbit of Mercury around the sun properly. The theory itself is a little hard to explain. His theory also explained several things physically. We all learned that the apple falls to the earth. We had a formula that said it falls to the earth. But Newton didn't tell us why it falls to the earth. That was left unsaid. So Newton didn't explain why it falls to the earth. But Einstein's theory immediately tells you that. If I look at this picture of the earth, and you see it distorts the space around it, you can imagine putting some object on this grid, and it'll fall toward the earth. And so the distortion around any mass is the attraction that was not explained by Newton, but is explained by Einstein of why the apple falls. So that's the first new thing that was explained by Einstein. He fixed the problem of mercury. His theory explained why the apple falls. That's pretty important. Most of us never thought of asking why when our teacher told us when we jump up, the earth pulled us down, and we believe that. The second problem is one that Newton recognized and wrote in the Principia when he wrote his theory of gravity, and that is he realized that his theory had what he called instantaneous action at a distance. What that means is when the apple falls and you watch it fall, you know that immediately. It doesn't take any time for the message to go from the apple to your eye. And that's fine for something like the apple falling. It doesn't really matter. But imagine that the sun were to disappear right now. We know that it would take 8 minutes for us to know that because it's the finite time that it takes the information to come to us, which in this case, in the case of light or heat, it takes 8 minutes. That's the speed of light. It also takes 8 minutes for gravity. In Einstein's theory, that's the speed of gravity, but at least it's a finite time that it takes the message to go from the action where it happens to the observer. And so these two things were newly explained by Einstein, and his theory became very important for anything where we started talking about high velocities and long distances, which is astronomy and astrophysics. So it became the theory for that. To make a theory accepted, you have to do more than just explain why the apple falls or something. Something new needs to be predicted. And he recognized immediately that the fact that there's a distortion of space around the Earth, which is a mass, that yes, it attracts the moon toward the Earth or attracts an apple to the Earth, but also it doesn't really matter whether the object has mass like the apple or the moon, that even if for something that doesn't have mass, it's going to have a trajectory that's affected by the distortion of space and time by the Earth itself. And so he recognized that if there were stars that went behind the sun, their light, when it came to the sun, when it grazed the sun, would bend a little bit. And you could see that bending. Well, if you take it the next step, you could possibly observe that if you looked at exactly the time when there's an eclipse of the sun and there's stars moving behind the sun, in which case that light would bend around the sun. That experiment was done with looking at a full eclipse of the sun 4 years after Einstein proposed this new theory of gravity, and that was in 1919 by Sir Arthur Eddington. He was Arthur Eddington, became Sir Arthur Eddington as a result of this. And that was a strange phenomenon for anybody to realize that light was going to bend and that had been observed. And that got picked up by all the newspapers around the world. And it was this phenomenon that made Einstein a household name, not the earlier work, which we as physicists had appreciated so much that he did in 1905. We celebrated Einstein in 2005, 100 years later, for all the work that he did in 1905. But it was the bending of light, actually, that captured the imagination of the people of the world, and that he became a worldwide figure. He actually visited here, and in, I think, 1921 or 22, at just the time this was known to the world. So another thing that happens, new discoveries in physics or in astronomy often become the tool that you can use to make science move forward, something that we couldn't do before. And it turns out this strange phenomenon of the bending of light is a phenomenon that's very commonly used now in astronomy to look at objects that maybe don't glow or that you don't see, because you can look at, as I show in this picture here, a source of light behind an object and watch the bending of light around it. We give that a name. We call it gravitational lensing in astronomy, and it's very commonly done. This is just some pictures of that being done. The last thing before I get to gravitational waves that I'd like to mention is that without Einstein's theory of general relativity, and the rest of this lecture may seem rather abstract, we wouldn't be able to use our little iPhones and tell where we are when we go down the road or walk. Actually, this ability that we have to locate is dependent on Einstein, and most people don't realize that. So let me show you that, and it's actually taken care of in the GPS system that we use to locate ourselves on our iPhones. The GPS system has, I think 24, the original one, 24 satellites around the world. At any given time, you tend to see 6 or 8 of them. And the signal goes up to them and comes back, and by comparing the length of time it takes for the different satellites and where they are, you can reconstruct where you are. And that's the scheme that's used. However, and this is where Einstein comes in, it turns out that these satellites are high up about in the sky, and they're moving pretty fast. They're moving 14,000 kilometers an hour. And that's fast enough to need relativity to describe what is happening with them. And when we study relativity as in class in physics, we learn something that tells us what happens, and that is that moving clocks tick more slowly. That's a phenomenon that happens. You have a clock and you move very fast, it goes more slowly. And of course, in science fiction, we use that to say that people don't age if you send them out as much, and so forth and so on. But anyway, the fact that clocks tick more slowly would screw up the ability to be able to reconstruct where you are in GPS if you didn't make a correction. That correction is made in the satellites. So we make a correction for special relativity. But I'm not talking about special relativity, we're talking about general relativity. It turns out that general relativity it also requires a correction. And that's because when the satellites are far enough above the Earth so that the amount of gravitational field that they feel is only about a quarter of what it is here on the surface of the Earth, and that causes clocks to move faster, not slower. And in fact, that correction is bigger than the correction that I just talked about for special relativity. If you put these numbers together, the GPS has to correct about 38 microseconds per day. And actually, if you put in the numbers to see what that means, how long if you didn't make that correction, how long would you stay on the road before you went off the road and didn't stay where you wanted to stay? It's just a minute or two. So this correction is absolutely essential to follow your road or do what you do. So if you don't appreciate anything else out of this lecture, you should appreciate that something you use every day uses a very theoretical principle that came out of physics, and that's general relativity. Okay, 1 year after Einstein proposed general relativity, he realized that there were some similarities between the equations that he had in general relativity and the equations of electromagnetism. He didn't derive from the equations of general relativity something new, but instead he just made an intuitive leap, and that is, since the equations had such a similarity to electromagnetism, and electromagnetism has waves, then gravity must also have waves. So in 1916, 100 years before we detected gravitational waves, he made this leap. He didn't prove it. And he wrote this little paper in German that I put up here, that gravitational waves must exist because of general relativity and the similarity of the equations to electromagnetism. The paper is not a very good paper. It's a very tiny paper, a few pages. There are mistakes in it. There's a mistake in the strength of gravitational waves, which would bother our experiment if we didn't do that, know that, and so forth. He wrote a second paper in 1918, 2 years later. And in the second paper, he fixed the error that was in the first paper. And he also told us how to make gravitational waves. We all learn that if we want to make electromagnetic waves, we take two charges and we oscillate them like my fingers are doing, and we make an electromagnetic wave with the two charges. That's the way they were discovered. And with gravitational waves, it takes 4 poles instead of 2, and that's the shape and so forth that we looked for when we looked for gravitational waves. So he told us how they were going to be made. Something that gives this so-called 4-pole thing is like 2 objects going around each other, or like a barbell that's rotating. And if you make them rotate and they're going fast enough, then the radiation will come off at the speed of information transfer, which for Einstein is the same speed as for electromagnetism. What we call the speed of light is also the speed of gravity. And what he showed is if I have 2 objects going around each other like this, they'll have waves going out. Those waves are just waves in space itself. They're not anything physical. It's just the same thing, a distortion of space itself, just like around the Earth. I showed you a picture of space being distorted. So that's what Einstein said. There was a lot of controversy about this whole thing. People didn't believe that there could be gravitational waves. It wasn't proven from the theory. And even Einstein, at some point, had some doubts because he couldn't calculate it from the basics of the theory. And it actually wasn't proven to the physics community until after Einstein died. Most people, he died in about 1952, I think. And in 1957, there was a meeting where most people think that that was where the physics community, or theoretical physics community, agreed that gravitational waves must exist. And that was a meeting called by a husband and wife who were general relativists, Cecil and Bryce DeWitt. And it was held in Chapel Hill, North Carolina in the US. And there were about 40 physicists, all of them experts in general relativity, that came to that meeting, and their challenge was to see if the gravitational wave, was the gravitational wave problem, are there not gravitational waves? A physicist named Pirani, a British physicist, at the beginning of this meeting, for the first time actually derived gravitational waves from the general relativity, from the theory, in a very elegant way. And so he's given credit for being the first one to actually derive that gravitational waves come out of general relativity. At the same meeting, Richard Feynman, who was a physicist who I knew well because he was at my institution at Caltech, but he was at this meeting as well, and he said in his characteristic way that if there's gravitational waves, whether or not they come out of the theory, they have to be able to do something or it doesn't really matter. They have to be able to do something themselves to be a physical phenomenon that's a reality in the physical world. And so he made what we call a Gedanken experiment. I show it here. And that is, if I have a bar and I put a couple rings on the bar and a gravitational wave goes through the bar, it distorts the bar just like distorting the space around the Earth. When it distorts the bar, it puts a little force on the rings and they move. Well, if they move because there was friction between the rod and the rings that are around it. And friction is basically a transfer of energy. There's heat, friction makes heat, and something gets hot. And so the combination of this physical explanation of Feynman and the theoretical one of Pirani, it gave us the belief that gravitational waves truly exist. So that's 1958 or 57. It was still another 50 years before we discovered gravitational waves. So the first 50 years was basically spent trying to figure out whether the theory was right, and the next 50 years trying to figure out how to detect them. So let's talk about how to detect gravitational waves. If you're an experimental physicist, what you get taught from the beginning is that if you do an experiment, in order to get a result that you believe, you want to make sure that you control all the variables. Anything that can affect the answer, you need to be able to control. So that was done, for example, in the first experiment that saw electromagnetic waves by Hertz. He started with a source that went up and down, two charges, went in the next room and saw a signal from electromagnetic waves, moved toward and away from the first room where the source was made, and saw that it had a wave-like shape, and that was the discovery of electromagnetic waves. So you'd like to do the same thing for gravitational waves. Have a source. In this case, the source has to be very strong because the waves are going to be weak, and you would like to then detect it some distance away. So I put in some numbers. Imagine that we tried to do this in our laboratory. I haven't made this as sophisticated as most laboratories. I put it down in a cave. And this man here has then a barbell, which will make a quadrupole moment. And I'm exaggerating. I put 1,000 kilogram weight on each end, make it a meter long, and then spin it. If I spin it, then it looks like that picture that I drew and can make gravitational waves. If I put these numbers in, just to compare it with what I'll show you we did in our experiment, you get an answer of 10 to the minus 35. The experiment that I'll show you, although everybody's impressed at how small a number we detected, detects a number in the same units as this of 10 to the minus 21. So in our experiment, the signal was 10 to the 14 times bigger than if we tried to exaggerate and tried to do it in the laboratory. So we were forced to do something that we're told not to do as experimentalists, and that is rely on something else where we might get fooled in nature to be part of the experiment that we don't have any control over. It turns out that we didn't have control over what created the gravitational waves, but we were lucky, and that is that they not only provided a much stronger signal, but they turned out to be tremendously interesting on their own because they were black holes, and seeing black holes collide for the first time was of great interest to people in astronomy and physics. So you can imagine a lot of different ways to make gravitational waves, and we look for all of them. I'll just mention that because what we found is the picture that you looked at, but we also could see, and I expect will see, gravitational waves from many other sources in the coming years. What I'll talk about is the top one, compact binary systems. What that means is two objects going around each other, like two black holes, two neutron stars, or the barbell, but it's not strong enough. A second possible source is supernova. That's the collapse of a star after it burns up all its fuel. And that would give gravitational waves, and we hope to observe that sometime and understand much more about how stars burn, how they react, what role gravity plays, and so forth. A third possible source, and this is not all of them, I'm just to give you some sense, would be pulsars in our own galaxy. Pulsars are spinning what we call neutron stars in our own galaxy. They give radio signals that people see in radio telescopes, and they give then a periodic signal as a radio telescope sees it in some given frequency. If they have this quadrupole moment, meaning that they're not perfectly spherical but have little mountains on them, then they'll give gravitational waves as well, and we would see periodic signals. Once we see those, which I'm confident we'll be seeing in the near future, then they keep spinning, so we can keep studying them in the future. Very different than the black holes that I'll show, where they come, they collide, and that's the end of the story. The last one is, I think, the most intriguing and the most interesting, which is that gravitational waves, at least in principle, represent the best way to find out what happened right at the earliest times near the Big Bang, something we don't really understand. So the problem is electromagnetic waves, where we do all our astronomy, as was shown by Dr. Yamamoto, only go back to about 400,000 years after the Big Bang. The universe was too opaque before that to go earlier than that, so we can study what it looked like in what's called the cosmic microwave background 400,000 years after the Big Bang, but we can't go earlier. We could go earlier with a particle that penetrated more like neutrinos, but we don't know how to do that. The neutrinos are very, very difficult to interact, and we don't know how to make a detector that would do that. That would go back to the first few minutes. If we are able to do gravitational waves from the very early universe, look at gravitational waves that were made in the very early universe, they would go back to the very first instance of the early universe. We don't know yet how to do that. We try to do it, but we don't expect to see signals yet. But I expect that in tens or 100 years, that will be done, and it'll be the ultimate way to understand the Big Bang itself. So that's the possibilities. I'm going to pick one of them, which is how we detect gravitational waves, in our case, from black holes. We made a target, or neutron stars, or compact objects. We made a target to do 10 to the minus 21. I told you experimentally, compared to 10 to the minus 37 if we tried to do something ourselves. So we have to find a source in nature large enough to make this tiny, tiny distortion of space. And if we look at then what the challenge is, what's going to happen? Imagine that we had a circle with some free masses on it, just free to move, but they're in a circle. Then if we had a gravitational wave go through, it'll distort it so it becomes an ellipse instead of a circle. And if it's got a frequency of once a second, it'll be vertically distorted and then horizontally distorted, then vertically, then horizontally, with whatever frequency the gravitational waves are. But if I take this 10 to the minus 21 and take 1 meter as the size of my circle, then I have to be able to measure an effect of 10 to the minus 21 meters. That's much smaller than anything anybody's ever been able to do. We make that number more doable by making a very big thing, not something 1 meter, but something kilometers. That brings the number of 10 to the minus 21 to 10 to the minus 18. So that's why LIGO's so big, was to make this 10 to the minus 28. The scheme then is to watch a distortion. I show it here once every half a second or so. It's going back and forth, where light, I'm going to show in a minute, comes from the left, goes and hits a mirror at 4 kilometers, both horizontally and vertically, If a gravitational wave comes through, the distances are different, and we detect that difference. If I put in the numbers of a real experiment, because I can't talk about all the things in the real experiment, there were two challenges that I would highlight that were the biggest challenge in being able to do this experiment. The first one is that we had to be able to tell the difference in this length, the two lengths, horizontally and vertically, to 1 part in 10 to the 12th of the wavelength of the light we're using. So we had a laser, and it has a wavelength. 1 part in 10 to the 12th of that was maybe 6 or 7 or 8 orders of magnitude better than anyone had ever done using interferometry. So we had to develop many, many advanced techniques and tricks to do interferometry at the level of 10 to the minus 12, the wavelength of the light. I don't have the time, or you don't have the background to understand all the tricks that we did to do that. The second thing, though, that we had to do is one that may seem surprising, and that is, despite the fact that we walk around on this earth and think it's pretty stable, it turns out that because we're working here on the earth is actually shakes so much that we actually have to reduce that by 10 to the 12th as well. So the problem is to reduce that by 10 to the 12th, and I'll show you how we do that. So the idea is that we have a laser beam. It comes and divides and goes in two sides. If the sides become different, the light it doesn't cancel. So here I've divided it. The light is in waves. It comes down and hits a mirror. It bounces back. If the two arms are exactly the same, one is opposite to the other and they exactly cancel. So there's nothing on the edge of my screen, the receiver. But if they come different from each other, they can add instead of subtract, in which case we see a signal. We have to make that little difference 1 part in 10 to the 12. So that's the scheme. The interferometry itself then goes from a simple picture that I show on the upper left to a rather complicated picture, which I show in the bottom right, and I'm not going to explain it all to you, but it took us more than 20 years to develop all the tricks and ability technically to be able to do interferometry to such accuracy. The second problem is a little easier to understand, and that is we also had to get rid of the shaking of the earth to 1 part in 10 to the 12th. This one you can understand what we did. First, let me say what the idea is. The idea is that somehow we have to take and make the final mirror, which is shown here in the center, stable against any shaking of the earth. And the shaking of the earth is then handled by two techniques, both of which you'll be familiar with. Well, what we do is basically what's done in an automobile. So in an automobile, when you drive down the road, you barely feel a bump when you go over it, a little sharp bump when you go over it. So what fixes that is the shock absorbers in your car. The shock absorbers don't get rid of the bump. In the first cars that were made, you went over the bump and you went like this. But rather, they basically take the bump, which is very high frequency and would make you bump up like this, and transfer it to very low frequency, and so you barely feel the bump when you're going down the road. And that we do, and so we made the world's fanciest shock absorbers, if you want, and we made 4 layers of them, which is shown here. And the 4 layers of shock absorbers enabled us to reduce the shaking of the earth to 1 part in 10 to the 10. But we had to do 1 part in 10 to the 12. To do the last factor of 100 was what eventually enabled us to detect gravitational waves. To do that, we used another common technique, and that is that most of you or many of you have familiarity with these earphones that people put on, say, in airplanes or in a noisy environment. They get rid of the noise. So in an airplane, if you put on these little earphones, the first ones are made by the company Bose, and the earphones make it quiet, and you don't hear the ambient noise of the engines anymore, but you can still hear the stewardess ask you whether you want coffee or tea or milk. And basically what it's doing is that the sensor in the earphones is hearing the ambient noise from the engines and canceling it. If somebody talks to you, it's not ambient noise, it's a spike, and so you can hear that perfectly well. So we basically use the same idea. We don't use Bose earphones. We don't use earphones at all. We use seismic detectors. We detect what the residual motion of the Earth is, and we push against it, make actuators that push against it and cancel it. So that was the final factor that enabled us to be sensitive enough to detect gravitational waves. When that was done, we were able to do it, and this is just the picture of where our two detectors are. They're 3,000 kilometers apart in the US. That's 10 milliseconds at the speed of light. This is what they look like. One of them on the left, toward me, is in high desert in the state of Washington, and the one on the right is in swampy forest in the state of Louisiana. They look very different in the picture because of that, but as instruments, they're identical, and we keep them identical so that if we change something on one of them, we immediately change it on the other one as well. This is the sensitivity then of such an instrument, and what's shown is all the lines which you can not pay attention to, but if you look at the shaded region, the bottom is the frequencies. So the frequencies that we're able to detect on the Earth's surface is what we call the audio band. We don't have anything to do with audio, but it turns out that by evolution, our ears, so we can communicate with each other, picked the place to communicate where the Earth is the quietest, and that's the band between 10 hertz and 10,000 hertz. So if we want to work in the quietest place on the Earth, we have to work between 10 hertz and 10,000 hertz, and that's the frequencies of the gravitational waves that we can detect on Earth. When we go into space, we can do different frequencies. So that's the frequency we do. The shaded region shows basically what we can detect, what limits us and what we can detect. And it's different in the different places. I drew all these lines, but basically we're limited by the shaking of the Earth, or at something I call seismic here, at the lowest frequencies, and we're limited by what we call shot noise, which is how many photons we have in the interferometer at the highest frequencies. So that's the scheme, and this is kind of the same picture in the detector itself. And you see in the different colors, they keep getting lower and lower on the line, and that's just making the detector better and better over a period of about 5 years. So this is what we did. Each time we found how to improve it, make it better, look for gravitational waves, not find any, make it better, make it better, make it better. So this is the process that we went through for about 7 years, and then we made a major improvement to the detector, and then we're able to detect it. So this is the major improvement that was made, making it a factor of 10 better than it was before. And it turns out that when we look for gravitational waves, we measure what's called an amplitude and not a power. And that means that when we have a signal that's half as big, it means it's twice as far out, but that's 8 times, because it's the cube, as much volume of the universe. So we gain very quickly if we can improve our sensitivity. So this is what we expect. I show on the left 2 objects spiraling, each of them spiraling themselves. They have a spin. They're going around each other. As they go around each other, they lose some energy each time around to gravitational waves. Eventually they merge together and then they ring down. And that's kind of what we were looking for. That could happen from neutron stars merging, could happen from black holes merging. And basically, we look for it by using what we call matched templates. That's taking Einstein's equations and calculating what the forms would look like for different masses of the two objects and different speeds. And then we compare these templates with the data, and we found gravitational waves. So this is the first figure from the discovery paper where we announced that we saw gravitational waves. So what you see here on the left, the scale, if you can read it, says 10 to the minus 21. So I told you that was the size that we would do. The bottom scale going to the right goes from, it takes 0.2 seconds, it's time. And so what you're seeing is the time evolution of the last part of a merger between two black holes going around each other and merging together at near the right-hand side of this plot. The top one is the picture of the data from the interferometer in Hanford, Washington. The middle one in Livingston, Louisiana. And then with a slight change in the timing, one on top of the other, and they look identical in the bottom one. They're not perfect shapes because the data has some residual noise. This is the plot that I looked at very early and convinced myself that what we were seeing is real. So the top two are what I just showed. The one on the left on the very top pane is the data from Hanford, Washington. The one in the middle here is the calculations of Einstein, and down here is subtracting one from the other. What you see is just a bunch of shaking, and if there was some other effects that it didn't agree perfectly with Einstein's equations, you'd see some sort of shape there. Instead, what you see is just the limitation in the experiment itself, that there's fluctuations that go across. So basically, that was the discovery, the first one. We then can calculate from that what it was. In this case, it was a black hole that was 36 times the mass of our sun, colliding with a second black hole that was 29 times the mass of our sun. And in the end, it made a merged black hole that was 62 times the mass of our sun. Notice that 29 plus 36 does not add up to 62, it adds up to 65. What that tells you is that the equivalent of 3 times the mass of our sun went off in the form of gravitational waves during this collision. So basically, that was what we saw for the very first detection of gravitational waves. We look at this for all kinds of effects. What I'm showing here is that we basically have looked to see whether there is any evidence for this having the equivalent of the photon for electricity and magnetism, what we call a graviton for gravitational waves. We see no evidence. We know how it would change the data that we look at, and instead we put a very, very tiny mass limit on what there might be if there was a carrier of this gravitational waves like there is for electromagnetism. In Einstein's theory, there is no carrier. We've seen now not one or two of these, but about 100 of them. If we look at them, this is just all of them. The scale on the left is the mass scale, and then there's all of them here. The ones on the very bottom are not black holes, but neutron stars. So we've seen black holes, neutron stars, and even a black hole colliding with a neutron star. We now have collected enough of them that we can do distributions of them. Why do we do that? We do that to try to understand now, which is what you do in science, the next step. Where do these black holes come from? Are they uniformly in the universe? Are they in the early universe? How were they made? How were they made into binary pairs? And so we get the distributions. In this case, this is the distribution of mass for them. And we compare with different models of how they might be made. And we haven't determined that yet, but that's the kind of thing we do that for the mass, for how they're spinning, for how they're oriented, all these kind of things. So if we get enough data, now we have about 100 events. When we have thousands of events, hopefully we can tell, for example, where they come from. There are 3 competing theories for where they come from. One is that they were what we call primordial, and that is that they were made in the very early universe and maybe account for some fraction of the dark matter. Or a second one is that they were made by some dynamical effect somewhere where you have small black holes and then they merge, and then other ones merge and so forth. And the third one, which is the one astronomers favor, is that the black holes come from the collapse of heavy stars. The problem with that one is that these black holes are so big that it's hard to have stars that are big enough to do that. So we have to resolve this experimentally, and we're doing that with the better data that we have. Now we're evolving into something completely different, which is where I want to end, and that is that maybe the most rich way to pursue this field in the future is to do the combination of studying gravitational waves and astronomy simultaneously. And we've done that a little bit. In order to do that, and I'll show you what we've done, but in order to do that, what we have to be able to do isn't to analyze this data in a very complicated way with Einstein's equations and blah, blah, blah. But we have to be able to identify that we've seen confidently, that we've seen gravitational waves quickly enough to tell astronomers to point to that place in the sky reliably, and then they'll see what electromagnetic radiation happened at that place in the sky. We had a lucky one, which I'm going to show you because they happen to be looking where we saw something. But what we have to do in the future is to do this quickly, and we're working very hard to do this. We have to be able to reliably tell and alert astronomers. If we alert them and say, whoops, we were wrong, they'll lose confidence in us, so we have to be able to do it reliably. This is a challenge, but I think one of the most productive ways that we'll combine what we know in astronomy with what we can learn in gravitational waves. And this is an example because we managed to do it for one case, and this is not black holes anymore. The first example of the collision of 2 neutron stars. Neutron stars are the product of stars when they burn up all their fuel and they're light enough, they collapse and make a neutron star. Sometimes, and we've observed quite a few in our own galaxy, they're binary systems, which means one captures and goes around another. This was a binary gravitational wave signal from 2 neutron stars that crashed into each other like the black holes did. But in this case, it turned out that a satellite experiment measuring high-energy gamma rays was looking at the same place in the sky. And so what I show here is the gravitational wave signal, which is this one. Whoops. I'm way ahead of myself now. Which is the gravitational wave signal, which is this down here, comes up as a line. And this is the detection of photons 1.7 seconds later. Interestingly, when we were able to take and look at this and see that it came from an event that happened 150 million light years away in a particular galaxy. 150 million light years away in a particular galaxy. An interesting conclusion, just looking at this, is that 150 million light years is 10 to the 15 seconds. So within 1 second, the difference between these two, we know that just from looking at this picture, we know that gravitational waves and electromagnetic waves travel at the same speed, to 1 part in 10 to the 15, just from this one observation. So in Einstein's theory, you expect them to go at the same speed. We call that the speed of light because, of course, we knew about light first. This difference, this observation was, as you see on the right, is basically the same location in the sky by both the gravitational waves and the satellite experiment. Following up on that, we were able to then confidently know that we had seen something in the sky that could be looked at by astronomers. So we announced it to the astronomical community, and more than 2,000 different identifiable astronomical instruments looked at this place in the sky over the next weeks and days and followed the evolution of the signal of this gravitational wave. So it was looked at first in high energy gamma rays. It was looked at then in the ultraviolet, in X-rays, in radio finally. And what happens is the radio comes last, that's the lowest frequency. Following all that and how much there is radiation there is in the different colors, we're able to determine basically what happened as two neutron stars merge. And that fit a particular picture of what we call a kilonova. Now, interestingly, when we do science, and this is another illustration, sometimes you learn something that's not really what you were aiming for, but maybe pretty important. I learned when I was a student that there was a puzzle, and that is that in the Earth, we find all kinds of elements, but we find ones we like a lot, like gold and platinum that are made out of, that are heavy elements, and we wear them as rings and jewelry and so forth. But we have no idea how they got into the Earth when the Earth was formed, because the universe is made primarily out of hydrogen and helium. And so the belief is it must have happened from the burning of stars. And as stars burn, there's nuclear physics. The nuclear physics of a star burning is the same process as what we call nuclear fusion. That's been proven many times. Fusion starts by burning light elements, hydrogen and helium, and then lithium and oxygen, and eventually you get up to iron. When you get up to iron, the fusion process doesn't work anymore. That's as high as it goes. And at that point, you're not burning anymore, which was an outward force on a star. And so then it collapses, and that's what we call a supernova. So that's well known. But what then isn't understood is how can the star, if they use the fusion process, produce gold or platinum or even the heavier elements? And so basically, as physicists do, we make a scheme for that to happen, which is called the R process that nuclear physicists use, but it was never very satisfying. Now we discover two neutron stars colliding, and in that collision itself, you can directly calculate what happens in that collision and what's made. And incredibly, in this given collision that we did, we produced, the one we observed, produced 100 Earth masses of gold. So, of course, that's not the gold that's in the Earth, but neutron star collisions in earlier times produced heavy elements like gold, which now, even on the basis of just one example, is our best explanation for how the heavy elements got into the Earth. And this is an example of how science talks to each other and how we are able to make conclusions about something very different than what we're doing. We entered, like has happened everywhere else, into what I call a pandemic pause and did very little because we do so much work that's close, but we weren't completely doing nothing. We did a lot of work and a lot of improvements, which I list here. And we expect to turn LIGO back on, where it'll be yet much more sensitive by this coming summer. So each step we improve, we'll be able to do more and make this new science of gravitational waves something that gets to be broader and broader in terms of the things we're able to do, how far out we can look in the universe. For me, the most interesting particular area is to be able to see far enough out into the universe to start doing cosmology with gravitational waves. Anyway, beyond what we're doing on the Earth, there's a specific experiment to do gravitational waves in space that'll look at lower frequencies than we can look at on the Earth. We look at what I showed you was the audio band. Even lower frequencies, I show here, can be looked at by looking at the pulsars that we know exist in our galaxy and looking at the timing of them. They're very accurate clocks, which gets distorted if a low-frequency gravitational wave comes in. So what I'm showing here, without going through it in any detail, is essentially the analog of what was, I think, the biggest progress in astronomy in the last 50 years. And that is when we did astronomy from Galileo's time, when he looked in the first telescope, until sometime in the 1900s, we confined ourselves to looking at the visible band, the same band of light that we look at with our eyes. The biggest advance that's made astronomy go forward, in my belief, since that time, over the last 50, 75 years, the last century, has been to look at astronomical objects at radio, ultraviolet, infrared, all the different frequencies. The same thing will be true for gravitational waves. I can tell you how rich we can do things on the Earth, but we're limited to the frequencies we look at on the Earth. But we have the ability to look at different frequencies in space, this thing that I show up here called LISA, even at lower frequencies using pulsar timing. And so we can look forward to moving more toward cosmology as we get more sensitive, looking further back in time or further into the universe. We can look at different frequencies. This is going to take some time, but this is opening a completely new field of physics. And with that, I hope I've intrigued you with this and you can watch it in the future. Thank you.